begin for the second half. So we're still in this idea of symplectic geometry, but today we want to speak about symmetries. Symmetries in symplectic geometry or in Hamiltonian systems. So there are these two main motivations. Like for physics, the motivation would be, well, whenever you have symmetries in your system, of course you would try to understand somehow how to reduce the phase space, because the phase space a priori is a very large dimensional space, but you can use symmetries to reduce this. And in particular, how do you reduce it? Well, symmetries, they will actually generate somehow conserved quantities. And so we'll really understand somehow how this correspondence works, this kind of Noether theorem, which gives you conserved quantities out of symmetries. And then you can, of course, use these preserved quantities to somehow simplify your phase space, because if you have an initial condition, you can just measure all these conserved quantities, and then you know, well, even if you don't know exactly how the evolution goes, you know that these quantities will be preserved. So in this huge phase space, there's this kind of submanifold where these conserved quantities have these values, and you know that you will actually stay inside. But as you will see, if you just take a submanifold in a symplectic manifold, it has it's very unlikely that it is symplectic itself. You have to do something a bit more in order to somehow get the notion of a reduced phase space, which should again be symplectic, because we want to still have our theory, like symplectic gradients and all this stuff. Okay, and from the mathematical perspective, this kind of symplectic reduction, it's actually a way to do quotients. So you have this category of symplectic spaces, and as for now, actually, we know very little examples, and more importantly, if you have several symplectic spaces, we don't really have much operations among them. I mean, you can take the direct sum or something, but it's not very interesting. So in order to somehow construct interesting examples, it's very important somehow to have this construction which gives you a quotient. Okay, so let's see the setting for today. We'll start with a symplectic manifold, always finite dimensional. And we'll take G, a Lie group. So typically in this lecture it will be S1, it might be SO3, it might be, what else? Well, GLN, SLN, R, or subgroups. But typically it will be some matrix group. So if you're not familiar with the general theory of Lie groups, I think from time to time I will make some remarks, but you can always think about, even like in the simplest examples, actually Rn, circles, maybe some powers of circles, tori, rotation groups, and matrix groups. Okay, then the Lie algebra, I will denote it like this. Lie algebra. So this is a vector space. It encodes somehow almost all information of the Lie group. And then the general setting is that we have an action. So G acts on this action. So in general, what does it mean to act? So there are different viewpoints. You could say that there's a map between G and the homomorphism group. You want this to be a homomorphism. So this means like, well, in the group you have an identity element, so you want this to act trivially, just by the identity on the manifold. And if you have two group elements, one acting by some diffeomorphism and the other by another diffeomorphism, then if you combine these two, then you just compose the diffeomorphism. Or equivalently, you want a map from G cross M to M. And I will denote it like this. So whenever you have a group element and a point, this action I will denote it by a point. So this means that G acts on this point. And of course you have some conditions which somehow translate this map to be homomorphism. So in particular, we have G1.G2.M. This should be G1.G2.M. Okay, everybody's good with that? Then we can start the first part, which is still more about these actions. I mean, this is kind of the general setting, what is an action of a group on a manifold, but now you should ask, okay, we have a symplectic manifold. So what does it actually mean to have a symplectic action? Symplectic action. As we will see, actually, there are several definitions, and they're not equivalent, so we will try to keep track of these definitions and to try to understand how they relate. So remember from last time, we saw these two groups, the groups of simplectomorphisms. So diffeomorphisms preserving the symplectic structure, F star F omega. And we have seen that there's a very similar group, but it's not completely the same. It's a subgroup. And I said that this is like the time one flow of a Hamiltonian vector field. Time one flow of its h for some h, some Hamiltonian. And I think this is typically what in physics we will call a canonical transformation. Canonical transformation is something which is generated by some function, typically the Hamiltonian. This is canonical transformations. I think math would just say it's a Hamiltonian diffeomorphism. And this was one of the properties last time, that when you integrate the symplectic gradient of a function, you preserve the symplectic structure. So this is why this is a subset of. Okay, so I have these two different groups, and then now when I take a group which acts on a manifold, well, you can somehow distinguish these two groups. So you will say that G acting on MW is called, well, symplectic, like a symplectic action. If in this viewpoint I don't end up just in general diffeomorphisms, but in symplectic diffeomorphisms. And well, we should call it Hamiltonian, but for some reason we call it weakly Hamiltonian. Weakly Hamiltonian action. If we have this map with these canonical transformations. So symplectic or weakly Hamiltonian. So let's see some examples. Two examples in particular, and you will see that actually it's kind of hard to really, I mean, the first part is kind of it's often not so difficult to see whether an action is symplectic or not, but to determine whether it's weakly Hamiltonian can be a bit more complicated. Let's say example one. Example one is SO2, two-dimensional rotations, I mean, it's just a circle, acting on a sphere by like rotations around the z-axis. Right, so I have this sphere which sits somehow inside R3, z, x, and y. And then my action is to turn around the z-axis. And yeah. So question, is it symplectic? Oh, I have not said, but S2 I will just take an area form. And last time we saw that whenever you have a surface, you take an area form. This is always a symplectic form. So is this action symplectic? Yes, why? Exactly. Yeah. So maybe these terms they seem very complicated, but in this setting it's very easy. Exact, in 2 dimensions, symplectic means area preserving. So does this rotation preserve areas? Well, of course. So yes, so it's a symplectic action. Symplectic action, since it preserves areas. Okay, before thinking about whether it's Hamiltonian, let's see the second example. 2. Which will be R acting on a cylinder, like S1 prime. By translation, so again you have kind of cylinder, infinite cylinder, X, Y, Z. And the action is by translation along the axis. Again, the z-axis, my action. Same question, is it symplectic? So again, cylinder with area form. Same argument, right? Just shifting a cylinder is area preserving. Symplectic, no problem. Symplectic, area preserving. Okay, so both actions are symplectic. So are they weakly Hamiltonian? So kind of these diffeomorphisms we get. So here we have rotations, here we have this kind of translation. Do they come from somehow the time flow of a Hamiltonian? You see, it's not easy. So we'll keep maybe this for 5 minutes. Maybe show somehow a kind of criterion. We can speak about like a tool which might help us to decide whether some action is weakly Hamiltonian or not. This tool is simply well, it's kind of this trick we always do when we have Lie groups. It's somehow to pass to a simpler object, to Lie algebra. So in this setting, instead of speaking about this kind of group action, you just consider the infinitesimal group action. So in general, when you have this action, you have G acting on M, general manifold. So this infinitesimal action, well, it is a map. So let's say this map from G into diffeomorphisms. So what is the infinitesimal version of this? What is the infinitesimal version of a diffeomorphism? Yes, a vector field. I mean, these are infinite dimensional objects, right? They're infinitely many diffeomorphisms, infinitely many vector fields. So it's actually, you should be a bit careful when you speak about kind of exponential maps and stuff like this. I mean, there are many, many vector fields which you cannot really integrate to diffeomorphism, even at very, very small times. There might always be points which crash together, but the other way around works. If you have a diffeomorphism, you can, especially if it's like a Hamiltonian diffeomorphism where you know it comes from a one parameter family of diffeomorphisms, then somehow you can take its derivative at 0 and get a vector field. But yeah, it's actually even true, like if you take a general diffeomorphism, it might not come in a family, even this, yeah, it's not very open. It's not very easy, the link between these two. But in the presence of a Lie group, somehow this is, any diffeomorphism comes in a one-parameter family. Since the diffeomorphism coming from a group element, you can always link this group element to the identity. Okay, so how I will denote this. So xi, I will denote this vector field by xi. So we should just keep in mind that, I mean, xh is the symplectic gradient, and xi is not a symplectic gradient, but, well, actually it will be in many cases. But, yeah. Okay, so now I have like a very similar definition, like what is kind of the infinitesimal version of a symplectic action, or a symplectic vector field. Symplectic vector field. So a symplectic vector field, well, it will be a vector field. It's like, it's denoted by this omega sign. So it's vector fields preserving omega. So it is a vector field such that when you keep a Lie derivative of omega, you get 0. So remember, the Lie derivative is kind of this infinitesimal version of this pullback. And then there's actually a nice, I mean, we have already seen it at least twice, maybe even 3 times. There's again this Cartan magical formula, which tells you that Lx omega is actually the same thing as taking the differential of omega and then evaluate it at x. So you have like 2 dots left. And you can also evaluate omega at x and then take the derivative of this. And then there's another dot left. And the first thing is 0 by definition. This is 0 since omega is closed. And so you can say that these symplectic vector fields, these are vector fields such that in this object here, the contraction of the symplectic form by this vector field is closed, because you want this to be 0. X is closed. So this contraction gives you a 1 form. This 1 form should be closed. Then this differential is 0, and then this Lie derivative is 0. And then once you have kind of this characterization, you can actually define the Hamiltonian vector fields. Hamiltonian vector fields, it's almost the same thing. But you want this to be exact. So I'm not sure if you're used to this terminology. Exact means it is the differential of something. You can write this as the derivative, the differential of some function. Typically we'll call it x h. And well, if you look at this definition, like omega of x dot is dhx, well, that's actually exactly the definition of a symplectic gradient up to some sign. So somehow this space of Hamiltonian vector fields is the space of symplectic gradients. Mark Hamiltonian vector fields is exactly the space of symplectic gradients for any kind of Hamiltonian. Okay, a small exercise for those who are interested. So a Hamiltonian vector field is automatically symplectic, but again, a bit like in this setting here, there are symplectic vector fields which are not Hamiltonian. There is kind of a nice thing that when you take two symplectic vector fields, like this, take two symplectic vector fields and you take their bracket as like vector fields, then this is actually an element, then you get a Hamiltonian vector field. But I think we will not really use this fact, but it's a nice fact. Okay, and then, I mean, why do we do all this? Because of the following property, like an action will be symplectic if and only if it's symplectic, sorry, if and only if its infinitesimal action is symplectic. And the same for weakly Hamiltonian. So P on MW is symplectic / weakly Hamiltonian if and only if G goes to symplectic vector fields or / G goes to Hamiltonian vector fields. So it seems that we have not, like, it's not very useful, but you will see it is very useful because like vector fields, they're much nicer behaved, and in particular, like you can, whenever you have an action, you always have this vector field, and then you just have to decide, is it a Hamiltonian or a symplectic vector field? So you just compute somehow this contraction here, and you can check whether it's closed or exact. So let's do this for these two examples. And we'll see what happens in order to decide whether they are weakly Hamiltonian or not. So maybe we should be a bit more precise, and we should write what exactly the symplectic form is. Here, back to example 1. So what is omega? So let's put maybe some coordinates. So we're on a sphere, so let's put spherical coordinates. Like if I have a point that should have two angles, Euler angles, so we know this by theta. And we take a projection. We have another angle here, which is phi. Let's say that the radius of the sphere is 1. So what is the area form? Yes. So usually it will be r theta, theta, wedge, and then you take the projection. The projection is cosine theta. Okay. No, I will sine. Oh yeah, this is the sine. Yeah. So this is the area form, and now you should think about what is the rotation. So I take alpha, an element of SO2. So how does it act? How does it act on a point which is given by in this coordinates? So you take this point, you rotate it by alpha. How does, for example, theta change? Yeah. Theta's constant, and phi. You just change this angle phi by alpha. Okay. So the associated vector field, so this action is psi associated to an angle alpha. I should alpha del phi. Okay. So now we should just have to check whether this is a Hamiltonian or symplectic vector field in order to decide whether the action is Hamiltonian weakly, Hamiltonian or symplectic. This together, and then for the second example, I give you some time to do it by your own, but we will somehow correct it. I mean, we'll see the solution together. So now, in order to decide, let's compute omega of psi alpha. So we take this vector field and we plug it in. D theta, it's sine theta, d theta, wedge d phi, and all this applied to alpha. So usually what would you do? You would apply d theta to this. But there is no del over del theta, so this is 0. And then you would apply d phi to it with a minus sign. So you get minus, you have this alpha, sine theta, and the only thing which is left is d theta. Everybody's okay with this?
Wasn't it d theta with sine theta?
Yeah, sine. Yeah, but I mean the sine is like a constant. You can put it out.
Oh.
Yeah. So the sine is a constant, and when I act d phi on this object, you get alpha. And since it's like the second entry, you have this kind of minus sign. And now you should ask: is this like is it closed? Is it exact? So closed would mean like if I take the differential of it, alpha is a constant. Like if I derive this with respect to theta, I get something non-trivial, but then I have d theta, wedge d theta, which is 0. And if I derive this with respect to phi, well, then I get 0 because it's independent of phi. So this is closed. But is it even better? Is it exact? Yes. So you should try to write it as d of something. Yes, minus alpha minus, we'll see, cos theta. So the derivative of cos is minus theta. So it's exact. Hence, conclusion, it is a weakly Hamiltonian action. And even better, actually we see now somehow the function we have to use. We see the Hamiltonian we have to use in order to generate this flow. Hence, weakly action. And somehow the Hamiltonian associated to this rotation is nothing but cos theta. And actually cos theta in now Cartesian coordinates is nothing but z. So maybe to just say it in different words, you take this sphere in 3D, it has an area form, so it's symplectic, and as a Hamiltonian you just take the height function, just this z coordinate. So this is some observable, you can declare it to be the Hamiltonian, so it will generate a flow, and the flow is the rotation around the z-axis. Actually you could kind of guess it, because I hope I said it last time. The symplectic gradient, so what does it mean to integrate somehow this, what does it mean to get an evolution out of a function? Well, you take its symplectic gradient and then you integrate the symplectic gradient. And I think we saw last time that the symplectic gradient, it points into the direction where the function is constant. So if I take the height function, symplectic gradient, it should point somehow in this xy plane. So you know it's some kind of a rotation, it might maybe have different speeds, but then you know that it should preserve the area. So actually the only way you can do it is actually by a rigid rotation. But somehow the computation we did here actually proves this on a more rigorous level. Taking the height function gives you this rotational flow. Okay, so now back back to exercise 2. Let's do the beginning together, and then I'll give you some time to think about it. Where is it? Here. So we have the cylinder. So what is this symplectic form of the cylinder? So let's take cylindrical coordinates. So point will be described by its z-axis, by its height. And once you project it down, it will be given by some angle. And I was always confused why we call this angle theta and not phi, but yeah, let's do it. This angle is called phi, theta. So yeah, it's not the same as this one. Okay, so in these kind of cylindrical coordinates, what is the form? What is the area? Again, let's say that the radius is 1. Z can vary freely, so it should be dz. And then I have something like r d theta. So r is 1, so it's just d theta. Okay. And then, so what's like kind of the vector field? Maybe let's write the action more precisely. So I take r as a number. So how does it act on such a point? Now you translate it.
Good question, actually. So does this discussion, I mean, does this depend on the choice of coordinate system?
No. I mean, deciding whether it's weakly Hamiltonian or not? No, of course not. But I mean, since it's a cylinder, it's kind of natural to take cylinder coordinates.
Yeah.
Yeah, you could do it with other coordinates, yeah.
Okay.
Okay, so what's the definition of this action? You take a point, you just shift it. So what are the new coordinates? Yes. R, theta does not change. Okay. So you should write this vector field. What is the infinitesimal vector field associated to R? Well, it just moves Z. The infinitesimal vector field. And then plug it in to the symplectic form and see whether it's exact or not. I'll give you some minutes in order to tell me.
Can I ask a quick question?
Yes.
Already in the example before, would we have said that the area form was exact?
The area form was exact? No.
We wouldn't have said it's like d of cos theta d phi.
But I think it cannot be exact. Let's see. Yeah, I mean, I agree that because usually on a compact manifold.
Well, that's like it degenerates. That's the issue.
Oh yeah. Okay, I see.
But here in the example, when we read
So that this is d of
it's cos theta.
plus cos theta d phi. Yes. Okay. Well, that's a good point. At some point we will see when the symplectic form comes from a potential, then somehow there are like very nice criteria to decide whether things are Hamiltonian or not. Yeah. Okay, let's keep it as a remark for now, but we will come back to it. Yeah. Is it the same for the cylinder? I mean, yeah, it's also exact.
Cylinder has no second cohomology.
Then this is locally, right?
Yeah, locally, that's somewhat the point.
It is locally exact, not globally.
Yeah, but
It's this like area of the sphere is here.
yeah, exactly. That was also my point. But theta is not a global coordinate, but cosinus theta is, cosine theta is. So I'm a bit surprised as well. Yeah, but it's surprising. I mean, usually a volume form can never be exact because if not, if you integrate it, you get 0. And by definition, a volume form is positive. So, yeah, probably something is wrong with this. Okay, but you should try to tell me whether, when you plug this vector field into the symplectic form, do you get an exact or just a closed form? You want to give the answer, or?
No, I want to on the question about, because I think that when there is a circle that shrinks, then the integral product with the generator of that circle must be vanishing at the point where the circle shrinks. So in that case, that doesn't happen because minus cosine theta d phi, if we take the integral product with the phi, with d phi, we get the minus cosine theta, which is non-zero at the poles. So I think that.
I mean, the problems actually come from phi, since phi is not defined on the northern side.
Yeah, I mean, phi generates an action which has 2 fixed points at the poles, and so basically it generates a circle that shrinks at the poles, and so for the differential form to be defined there, the contraction with the generator must be vanishing at the poles, and in that case doesn't.
I'm not sure to understand, but I mean, this is actually a point. Like phi is not well defined on the poles. So. Actually, the expression we wrote somehow it's like, yeah, it's more or less a local expression.
d phi, which is not defined on the poles.
D phi is not defined on the poles. Well, phi not as well. No, I mean, phi
Yeah,
can
but
be
that-
0 or 2 pi.
Yes, but in particular also.
In particular, d phi, yeah.
If it were like a sine of theta times d phi, then it would be okay. Because
In the cosine is 0, so you have 0 times something which is not.
sine is-
No, sorry, cosine is 1. But the area of, I mean, omega for theta equals 0 is 0 as well. We said that omega should be non-degenerate. So. Yeah, this formula holds apart from when sine vanishes. So this formula holds only when sine theta is not 0.
I would say yes.
The general opinion? Just closed. Yes, what?
It is exact.
What should we compute? Omega xr. So we should apply this dz wedge d theta to this vector field r del z. R is just a constant, you can put it out. So dz acting on this vector field gives 1, and d theta acting on this gives 0. So you just get r d theta. So this is of course closed. If I apply another d squared is 0. So the question is this exact?
No.
It seems to be, right? It seems to be d of r theta. So it's d of something. But somehow the question is this something a well-defined global object on our cylinder? No. Theta is just a kind of a local coordinate, right? If you go around, then you get a problem with 2 pi. That's maybe. Yeah, that's actually the subtle point of this example is that, yeah, it seems to be exact, but actually it isn't. Mention theta is not a well-defined global function on the cylinder. One. And so, actually, it is not really Hamiltonian. Somehow what this computation gives is, well, if you want to generate this kind of shift in the z direction of a cylinder, you should take as Hamiltonian theta. But theta, again, is not a well-defined coordinate. You start somewhere, you say, well, here theta is 0, and you go around, you go around, and then you would say, well, actually, theta is also 2 pi. But 0 is not 2 pi. So this somehow is this. And there's actually a remark, which is kind of very general, which kind of is like a deep result in Hamiltonian diffeomorphisms, like a canonical transformation. Hamiltonian diffeomorphism, like in physics term, canonical transformation, cannot displace, in English, cannot displace a compact Lagrangian. So in our example, we have the cylinder. And I mean, what is a Lagrangian? Lagrangian in 2 dimensions is actually any kind of curve. So for example, if you take like kind of this equator, this is a compact Lagrangian, and if this flow would be Hamiltonian, well, it would just put it up. It would displace, I mean, it would shift this Lagrangian. But somehow there's a very general result which states that whenever you have a Hamiltonian diffeomorphism and it acts on a compact Lagrangian, then you have fixed points. So in general, this is called the Arnold conjecture. It was proven in many Arnold conjecture, which was proven in many cases. So when you have a Lagrangian which is compact Lagrangian, and you have a Hamiltonian diffeomorphism, then take the intersection between L and phi of L, then like, the number of points in this intersection is at least, well, it's at least, to be exact, it's the sum of Betti numbers of L. For those who know what it is. But just to say that this is at least 2. So you could ask the same thing for the sphere. So you take a sphere. Well, again, any kind of curve is Lagrangian. So let's take like a big circle. Well, if you now rotate the sphere, well, you always have 2 fixed points, north and south pole. So you get exactly this kind of 2 fixed points. Yes?
What is roughly the reason why this?
Oof, it's very complicated. Well, this kind of inequality, you typically have it for a Morse theory. Like you have a manifold, you take a Morse function on it, the number of critical points is, well, like somehow you can build up the cohomology out of this function, so the number of critical points is at least this kind of sum here. So what this says somehow is that when you take a Hamiltonian diffeomorphism, it should behave a little bit like a Morse function. And the reason somehow, very deep reason, is that you should go from the manifold to the loop manifold, like the space of all loops. On this space, you can define kind of a function whose critical points are exactly the fixed points of this Hamiltonian flow. So the fixed point of the Hamiltonian flow should correspond to some critical points of some function, and so by the Morse theory, these Betti numbers should appear, and the only last thing you need is somehow the Betti number of the loop space is, I'm not sure if it's plus or minus, there's like a link to the Betti numbers of the base. So think the very rough idea of this kind of theorem is you should go to the loop space, which is infinite dimensional, and you have actually to do a Floer homology, but somehow this is.
Also another, I don't know if I missed it, but what is the Lagrangian on a manifold?
Okay, well, yeah, maybe I have not said it. I mean, it's a submanifold such that at each point you can take its tangent space. You take the tangent space of the huge manifold, and then it should be a Lagrangian submanifold as a linear vector space.
Okay.
So in particular, it's a submanifold which is of half dimensional. Yeah, very good question. Thanks. Sorry, I forgot. Okay. More questions? Okay, so now we've seen these kind of two notions, Hamiltonian and weakly Hamiltonian. Symplectic and weakly Hamiltonian. But so you see there should be also the notion of a Hamiltonian action, which is a bit stronger than the weakly Hamiltonian action. So how does this go? So when we have a weakly Hamiltonian action, G weakly Hamiltonian, what does it mean? It means that any group element here gives you a Hamiltonian diffeomorphism, so in particular you can associate a function, like the Hamiltonian. So we get actually a map, which from psi, element of the algebra, should give you an element, which is psi, in the function space. So what should it, like what's the definition somehow? So when I compute the vector field associated to this element, this should be the symplectic gradient of this function. Okay, so this is very natural. I mean, you have a symmetry, and every symmetry should correspond to some function. This function should generate this symmetry. But now you have actually a nice structure on both spaces, G and the space of functions. So on G, well, you have the Lie bracket, and on the function space, you have the Poisson bracket. And as we have seen, Poisson brackets, they are Lie brackets in particular. So the definition of the Hamiltonian action is as follows. G x W is called Hamiltonian action. Hamiltonian action if, well, if it is weakly Hamiltonian, but you want a bit more. If it's weakly Hamiltonian and kind of this map from G to C infinity of M, which to psi associated with the Hamiltonian, is a Lie algebra homomorphism. Well, this is kind of a big term, but it just says the following. You can, if you take H associated to the bracket of two elements, you take two elements in the Lie algebra, you take the bracket, you take the Hamiltonian associated to it. This should be the same as taking the Poisson bracket between H psi and H. So this should be satisfied for all psi in the Lie algebra. Okay, maybe one comment, an important comment, like, is this function, is this Hamiltonian, like say it exists, I mean you know, if it's weakly Hamiltonian, you know it exists, is it unique? Yeah, so I take this kind of Hamiltonian, I know it exists, but is it unique? I fix my psi, is this H psi defined by this equation, is it unique? Because we saw somehow that the symplectic gradient is like well defined, but somehow now I do the opposite. are there different functions which give the same symplectic gradient? Exactly, yeah. So you can always add a constant, right? It's like kind of like if you have energy, I mean energy is always a relative thing. You can like put your zero level as you want. So actually, maybe I should write this over here. So h psi is defined up to a constant. Up to a constant. And somehow this relation tells you that you can make a choice of all these constants such that this equation holds. So all these things, again, kind of very complicated. So there are like very nice theorems which actually tell you that in many cases it's like automatic to be Hamiltonian, or like you don't have to check this every time. But before giving you the theorems, just going back to example 1. Example 1 is still on the blackboard, I hope. Yes. So we have this kind of Hamiltonian Z here. So you should ask whether this property holds. So in example 1 we saw, so you have it SO2, which is actually a circle. So what's the Lie bracket in there? What's the Lie? What's the Lie algebra bracket? It's just R, so trivial Lie algebra. There's no bracket which is non-zero. And we saw that when I take an element alpha in SO2, we saw that H alpha, well, yeah, H alpha of a point, XYZ, in the sphere, we saw that this is nothing but alpha Z. Or alpha cos theta. So you should check. So if I take two elements now and I take the bracket is 0, so the Hamiltonian associated to it is 0, you should check that when I take two functions of this form, their Poisson bracket is also 0, but of course this function only depends on theta. So if I take now alpha and theta, sorry, actually I should write it more like this. This is actually Lie algebra. Yeah, actually, this I will call it, or I try to write it as SO2, like a small s, O2. So if I take two elements, then their bracket is 0, so h of alpha beta is 0. That is also alpha cos theta together with beta cos theta. The bracket, the Poisson bracket is also 0. So this relation holds. So the action of example 1 is actually even Hamiltonian. So example 1 is symplectic, weakly Hamiltonian, and even Hamiltonian. Example 2 was symplectic, but not more. So now I just want to give you some very general results, which are deep results, but they will help us a lot. It will allow us not to do all these computations all the time, just refer to these results without doing computations. So questions so far? A bit abstract for now, but I promise you will soon see the light at the end of the tunnel, which is like the understanding of the Noether theorem. So I hope this is kind of nice motivation. So there's the following theorem. If the first cohomology group of your manifold is 0, or if the first cohomology group of your Lie algebra is 0, then like a symplectic action is automatically weakly Hamiltonian. point is if the second cohomology of G vanishes, then weakly Hamiltonian action is automatically Hamiltonian. Maybe a remark for the second statement. So I said like somehow these Hamiltonians, they are defined up to a constant. So of course you can choose some of the constants such that sometimes these relations hold. But some of the question is like, can you fix all these constants such that it holds for every element? And actually if you write somehow the difference between this and this, then you get actually two co-cycle in the space of kind of constants. Two co-cycle which depends on two elements of the Lie algebra, which is their constant value. So probably I should put like R here. And so this statement means that when there is no co-cycle, like if all these co-cycles are co-boundaries, then actually you can always find a choice such that our relation holds. Okay, so this, well, is a very general theorem, but it's even better. There's kind of this lemma. Yes, well, this is like cohomology. You have seen some kind of course of cohomology, but I will not assume that you know a lot about cohomology, but there's this Whitehead lemma, which simplifies things even more. It says the following: if G is semi-simple, so semi-simple means that the killing form is non-degenerate. Killing form is non-degenerate. But since I said we should not, or will not speak about general Lie groups, just about concrete examples. So in concrete examples, it means that it's a non-abelian. Typically it should be a non-abelian matrix group. Non-abelian matrix group. Like SLN, SON, all these things are semi-simple, but not SO2. SO2 is abelian. So whenever you have a semi-simple group, then actually these two homologies, H1 and H2, vanish. So in particular, if you have a physical system where the symmetry is such a group, which happens a lot, like for example rotations, like rotations in 3D space, SO3. SO3 is semi-simple, and then you automatically get that if you have a symplectic action, you are immediately Hamiltonian. It's automatically Hamiltonian. Okay, I think it's time for another example. And all the examples I give, they look very simple, but I mean, somehow the power of this formalism is that it's very general. It does not only hold for these simple examples. So let's take as a group R2, which acts on R2 just by translation. Let's say x naught, y naught acts on xy by x plus x naught, y plus y naught. So the question, is this action symplectic? Is it weakly Hamiltonian? Is it Hamiltonian? Is it symplectic? Does it preserve area? Okay, so is it weakly Hamiltonian? Yes, why? Without any computation? Is the group semi-simple? No, it's abelian. We cannot use this. But what else can we use?
First cohomology of
Yes.
R2. Yes.
Since each one of R2 is trivial. Okay, so we can immediately appeal the reference to this theorem. We know it's weakly Hamiltonian, since it's symplectic. Symplectic implies weakly Hamiltonian. So the question is it Hamiltonian? I really like this example because, I mean, in physics, very often all kind of examples you encounter are nice, right? Every function is analytic with the stuff. So all the nice examples should always be Hamiltonian. And this is a very, very natural example, right? So it should be Hamiltonian. But there's a reason why, we define all these kind of concepts, because it's a bit more complicated than it seems to be. So what should we check? I mean, we should really somehow compute Hamiltonians. So shifting in the x direction, what is the Hamiltonian of this?
Yeah, coordinate.
Y, yes. We can check this. So, okay. So h of x, I mean, actually, to be exact, it should be y. So y, because if I take the symplectic gradient of hx, there was kind of this formula, you derive with respect to x, and then you get del y, and then you derive with respect to y, where you get this one sign, and you get del x. So this is exactly the way going to the x direction. What is the Hamiltonian of y? Minus x. Minus x. Oh, for some reason. Okay, so now we should check whether this relation holds. So what's the Lie bracket of x and y? 0. X and y, the Lie bracket is 0, since R2 is abelian. So the Hamiltonian associated to this is 0. But if I take the Hamiltonian associated to x and the Hamiltonian associated to y, and I take the Poisson bracket, so I get the Poisson bracket between y and minus x. Y minus x. This, I mean, the Poisson bracket in this case should be something like derivative with respect to x, where it's derivative with respect to y. So this is typically something which should be 1. So it's not Hamiltonian. Not Hamiltonian.
But we can choose the Hamiltonian of 0 to be 1. Is a constant?
Ah, okay, you say like everything is defined up to a constant, so we should put this to equal to 1. Okay, it's a good point. I think then you run into other different troubles, because, yeah, for example, you can take twice x here, and then you get a 2 here, and you get a 2, and then 1 should be equal to 2. So you will never be able to fix this constant. Yeah, but yeah, good try. I mean, yeah, this relation, that's important. This relation should hold for all psi and eta. Yeah, if I just scale x here, I would just scale this number. So even if I fix this not to be 0, but to some constant, it cannot be a constant scale. actually, I can maybe do the remark at this point. I want maybe a bit later, but there's actually like procedure. Like when you have a weakly Hamiltonian action, actually you can always produce a Hamiltonian action by changing slightly your group. What you have to do actually, you'd have to take your group and you'd have to add one variable to it. So, and this new variable should commute with everything we had before. So it's called a central extension. And this new group would actually act then in a Hamiltonian way. And in the case, like in this example, what you get, like when you do this construction, you will get a group which is one-dimensional bigger than R2, and it's actually the Heisenberg group. Somehow, one reason why like Heisenberg algebras appear a lot in quantum mechanics comes from this fact. That's kind of translations, which is a very natural object. Like translations are very natural, but this action is not Hamiltonian. The somehow group you should consider is the Heisenberg group, which is the central extension of translations. So if G, X, and MW is weakly Hamiltonian, then there is a unique, the symbol means like there's a unique central extension, G hat. I will not define exactly what it means, but I mean, it's kind of, yeah, you take your group G and you add like a copy of R, say. This copy of R is central, so the Lie bracket is 0, but still it might, it's not the trivial product. There's like a unique way to define this group such that the action of this new group becomes Hamiltonian. So there is a unique solution such that, so I have to finish this, G hat X MW in Hamiltonian way. And in the example above, you would actually get, G is R2, X equals the Heisenberg algebra, Heisenberg group, 3, and it is actually R2, well, it's a semi-direct product with R. It's not a direct product, it's a semi-direct product. Semi-direct. There was a question. Yeah.
So this exists with the
Yeah, unique means it.
and this means there exists exactly one.
Yes, exactly.
Right.
There exists exactly one. Yeah.
Thank you.
Sure. Yeah. There is such an extension and it's unique. Okay, so now let's see kind of this a bit of perturbing example, which is so natural, but somehow which is not Hamiltonian. So there's like a last step, the last definition. I think we're done with definitions. No, it's not completely true. So there's last definition, which simplifies even more. So as I said, like in many different contexts, especially in physics, like in physics, the typical symplectic manifold is like a phase space, like a cotangent bundle of some manifold, T star of n. And for T star of n, well, the symplectic form actually has a potential. It is exact. And in this case, so if our manifold is actually exact, it's an exact manifold, it's an exact symplectic manifold, is exact symplectic, well then I can define what is called an exact action. Then such an action is called exact. It's called exact. Well, if the potential of the symplectic form is preserved. If G star theta equals theta of all G. So there's a slight abuse of notation, like G is an element of the group, but I see it as a diffeomorphism. Okay, and then the very nice property is actually when you have this exact action, then an exact action is automatically Hamiltonian immediately. Exact action is Hamiltonian. Oh no, yeah. For example, if you take this example here, let's do this example again. Back to example 3. So R2 omega is dx wedge y. So this is of course exact. For example, you can say it's d of x dy. You could also say it's d of minus y dx. And there were different ways to write this as an exact form. So you can ask, well, is this one form preserved, or is this one form preserved under this translation action? This one, for example, of course, is invariant if I translate y, but it will change if I translate x. And this one is the opposite. This one is fixed if x changes, but not when y changes. Unfortunately, somehow, we have to make a choice, and we want, once we have done this choice, we want to have this for all elements. Even if this is like invariant under y and this is invariant under x, well, each of them has some non-invariance. This typically is not an exact action. Not an exact action. And this is actually good because we have seen that it's not Hamiltonian, so it cannot be exact. Okay, and then maybe just one last example before we make a break. What's actually what's the typical situation in physics? How do you get actually symmetries in physics? Well, I would say maybe there are other ways, but I think the most natural source of symmetries is when your configuration space is already symmetric, right? Like if your configuration space is symmetric, well then of course also your phase space is. This kind of example / exercise. So let's consider any manifold. So you should think about it as a configuration space which has some symmetry, G X. And any action. So then actually it's not hard to see that there is an extension, there's an extended action, G on T star n, phase space. Phase space. So how does it work? How does it go? Well, T star n, well, you have one direction which is the manifold direction, so you know how to act. And then you have kind of these cotangent fibers, they're linear spaces. So when you have a group element, you can kind of pull back, and you take just this pullback action on the fibers. Okay, so you can write it in coordinates. I mean, you can write it, action given by. So if I have G, which acts on a point and some element of the phi, like an element of the cotangent space, so phi should be an element of T m star n. And this is in it follows, well, you act on m in the usual way. And on phi, you should pull it back, but you should pull it back. I mean, it should be a point at Gm, so you should actually pull back G inverse. Take its derivative and pull it back. kind of the mathematically complicated formula, but I think in coordinates, I mean, okay, and then the proposition is that this action is always exact. This action is exact. And in particular, by the proposition there, it's in particular Hamiltonian. In particular Hamiltonian. So again, if your symmetry comes from a symmetry of the configuration space, then you don't have to do any computation. We know that the action is Hamiltonian. For example, if you have a rotational symmetric system like hydrogen atom or something like this, so SO3 acting on configuration space, for example, SO3 acting on R3, and then SO3 also acts on T star of R3, which is R6, so you have XYZ, and the momentum Px, Py, Pz. So this action is automatically exact. Okay, so what we see in the second part is, well, once you have kind of a Hamiltonian action, in particular if you have an exact action, you have kind of this collection of conserved quantities, which we call the moment map. And we'll see what we can do with the moment map. Okay, so we should resume at, well, actually we started a bit later, but should we resume at 11? Okay, let's start again. So, for me now the really cool stuff starts, because now we have all these kind of vocabulary about these different kind of actions. We really can try to understand symmetries. There's this Noether theorem, probably most of you have seen, which, well, informally says something like, to each continuous symmetry is associated a conserved quantity. People typically say, well, for example, physics as a whole, applied to the universe somehow, the laws of physics should be invariant under time. You have a symmetry, time symmetry, and the associated conserved quantity would be energy. Energy conservation comes from physical laws being invariant under time. Or another typical example, time invariance gives energy conservation. Or another example is when you have a system which is invariant under some translation invariance. And what you get is momentum conservation. So here, I mean, the setting is more general, so we have again this Lie group acting on the symplectic manifold, and we say it's Hamiltonian action. This is the assumption we really need, Hamiltonian action. And then somehow we'll define what we call the moment map, but you should really think about it as the collection of all conserved quantities. So collection of all conserved quantities is called the moment map. So now we can kind of give the exact definition, but I think, I mean, you will be probably surprised as much as I was surprised when I saw it the first time. So again, we are in this setting. G acts in a Hamiltonian way on a symplectic manifold. And then the moment map is the following. So we call it mu. So it is a map from M somewhere. I mean, that's okay. So M, of course, like the idea is like to every point of your space, which is kind of your phase space, you associate the list of its conserved quantities. And the surprise is somehow the space where it lands. I mean, you would say it's just a list of things. Well, it is some kind of list in some vector space. And somehow the surprise is that this vector space is actually the dual Lie algebra of the symmetry group. So this is really like this is the dual Lie algebra. And dual really in the sense of linear algebra, like linear functionals on the Lie algebra. And how does this map go? Actually, when you write it down, it's pretty natural, but it's always a bit mind-boggling to like try to use it. So to a point, I will associate, well, it should be the collection of conserved quantities. And actually, these conserved quantities, they are indexed by the Lie algebra. That's what we said earlier, somehow, like to an element of the Lie algebra, I can associate this Hamiltonian. You see, the Hamiltonian is indexed by the Lie algebra. So here it's a map which, to an element of the Lie algebra, will associate the value of this function. Maybe you just read this line. So to a point, I want to associate the list of all conserved quantities. This list is this list of h psi m. And the index set psi is all the elements of the Lie algebra. Somehow what you can check is that this map, now seen as a map from psi to h psi, is actually linear. That's why it's kind of the linear map over the Lie algebra. Okay, and one like important remark is somehow how many conserved quantities are there? So the dimension of G star, well, that's the dimension of G. So this is kind of the dimension, it's like the number of, let's say, independent conserved quantities. If I just say number of conserved quantities, of course it's infinite, but I mean if you have like energy, then also twice the energy is conserved, 3 times the energy is conserved, and so on. So it's really like this notion of independent conserved quantities, which is important. So the dimension of conserved quantities, or the number of independent conserved quantities, is equal to G, which somehow is suggested by the Noether theorem, right? Like to each continuous symmetry, for every direction in your Lie group, you get one conserved quantity. And when you have independent directions, the number of independent directions is kind of the dimension of the Lie group. So good? Probably in order to better understand what happens, let's use an example. Well, the simplest example we can imagine is R acting on R2 by, let's say, x shift. So P dx here, and let's say that R acts on Px by P R. So this is the x shift. So we've already seen that we have not really exactly seen this, but well, it's symplectic, of course. It's symplectic since it preserves areas. So the Lie group is, well, actually, I think a good thing we should say is it's exact. It's an exact action. So this, you can write it as d of Px, right? So it's an exact manifold. And when I shift x, then P dx is invariant. invariant. So exact actually. So the action is exact, so Hamiltonian. And the Hamiltonian, included it, I think, so HR at the point Px. When you shift in x, you should actually take a Hamiltonian, which is T, and then somehow in order to shift by r, not just by 1, you should scale it by r. Okay, so this is the Hamiltonian, and now let's try to write the moment map. So u should go from R2 to the Lie algebra. Well, Lie algebra of R is R, and it should be the dual R star. With Px, it should associate what? So it should associate kind of this number, HR of Px. But as you see, there's an R dependence, so it should actually, to R, it should associate this. Okay, so again, it seems very complicated, but well, so this is R times P. And then, actually, you can identify, let's identify R star with R. In which way? I mean, if I have a linear functional, I can just evaluate it at 1. And you can actually check that this is an isomorphism. So I want to identify this with just a real number. So I would just evaluate this at R equals 1. So you just get P. And then the moment map of Px under this identification is just P. And this is actually probably what intuitively which we would say, right? When you have a symmetry, which is translation in x direction, then the associated conserved quantity is the momentum. So the usual momentum. And this is actually why it's called momentum map, moment map, because it's, in very concrete examples, you either get like momentum, and you will see there's another example where we get angular momentum. So in general, these kind of conserved quantities are like generalized momentum. Okay? So as I said, very often in physics, you are on an exact manifold, as it was actually the case here. And in this case, there's actually a nice formula for the moment map. The proposition will give you the formula of this moment map, somehow, of the set of conserved quantities again, in the setting of an exact action. If G acts on M omega, which has a potential, a global potential, is exact, then, so we've seen that exact implies Hamiltonian, so we can ask what is the moment map. Then the moment map is given by mu. Well, actually, I might actually, very roughly speaking, it was just a mu equals theta applied to x. Maybe this is too. I should put more. Yeah, so I should write mu of m. So first I should write mu of m. So it takes a point of my manifold, and then it should take some element of the Lie algebra. So it should act on some element of the Lie algebra. And what somehow this formula tells us is we should take this one form, x to the point m, and we should evaluate it at the vector fields associated to psi at the point m. So this is somehow. So this is So let's see what happens in this example. Back to this example. So back to the example, we saw that omega x. So this is theta. So mu at the point xt is applied to we call it r should be this form p dx at the point px, or px. Yes, and you should evaluate it at the vector field. Well, the vector field you always have to compute it. Have we computed it here? Oh, actually, we have not computed it here. Well, it's a translation action, so the vector field should be r del x. So del dx del x gives you 1. So it's exactly what we saw here. Okay, so as I said, let's take another example where you get angular momentum. So let's take this example. So let's take SO3 acting on C star R3, like diagonally somehow. Diagonally. This is actually the extended action of SO3 just acting on configuration space. So we know already that this is exact. Exact. Since extension of SO3 acting on configuration space. So we know it's Hamiltonian and we can use this formula in order to get the moment map. Okay, so we should find the thing. So what is omega? So omega is the usual standard structure, dpi dxi. So we have a choice somehow in the potential, but let's say it's the sum of pi dxi. So this is our theta, differential one form. And the other thing we have to determine is the infinitesimal action. Maybe we should write down more clearly what we actually do. So we have SO3. So how does M actually act on like a vector and the momentum, like the momentum vector? So these two things, somehow we can identify them as elements of R3. So the rotation action is really just taking this matrix and apply it to these two vectors. Okay. So how do you determine infinitesimal actions? This is for the Lie group. So now infinitesimal action. That's actually like a general thing you can do. You should put M equals identity plus epsilon something else. And now this something else is actually an element of the Lie algebra, SO3. So it's a small SO3, Lie algebra. And somehow you compute this action and you just look at the first order, and the first order should give you this vector field. In this case, it's pretty simple. F1 plus alpha applied to Vp. Well, what you see is simply Vp plus epsilon AB AP. So actually, somehow the infinitesimal action is actually the same as the global action. So this somehow is our vector field. Let's call it xi I at the point V. So this is the vector field of the infinitesimal action. So now we have these two ingredients we need for this formula, right? We need theta and we need the vector field. So, by the proposition, what do we get? So mu map it like a point, and then it takes an element of the Lie algebra, so here I call it A. And what should it do? So it should take theta, this one, so sum pi dxi, and you should apply this to vector field. The vector field is A, B, A, T. Maybe I should. So the dx part, the dx part tells us that we should only consider the x, x y z part, so only this part. And then we should apply p to it, right? So this is somehow p as a vector somehow applied. P as a linear form applied to AB. Let's make this here, but here P is really seen as a linear form. But if I want to see it as a vector, then I should probably take something like scalar product, right? P scalar. So now I see P as a vector again. Okay, and then you can check. So this, I know this is an exercise. We could say that we are finished, right? Like, one map is this. But you can check that you can write this as A applied to P cross product with B. And then somehow I can forget about A and I can just say that hence the moment map at P and V is this cross product P cross V, and this is angular momentum. Angular momentum. Okay, so good. We find the usual things we know from conserved quantities. We see momenta, we see angular momentum. But again, this is kind of much, it's very general. Yes?
The vector fields, these are pointing in so first of all, V is just X vector, it's the same thing?
Yeah, V is like X, Y, Z.
Okay. Yeah. And then the vector field, there's some DDXIs.
Yeah, I think if I want to be precise, I should say something like, actually XA, there. XA should be something like AV. But there should be some del X, del Y, del Z.
DDXI or something.
Yes, but how should I write this? In coordinates it's kind of clear, right? I did X with X, then you should, A11, then you have A12, Y, then you have A13, Z, all this del del X, and then you do it again for del del Y, del del Z. I think you should write it like this. Yeah, applying a matrix to V gives you 3 entries, but actually it's a vector field, so that's del del X, del del Y, del del Z. Yeah, maybe this is a bit, yeah, I should maybe write it more cleanly, more clean way. No, actually you can, oh yeah, sorry, what you can do is, like in this case, R3, I mean, you can identify a vector field actually with a vector. If it's a constant vector field, is it a constant vector field? No, but you have R3, you consider just one point, so a vector field at this point is just a vector, and I claim that this vector is given by A. I mean, yeah. Or like, well, if you take the total phase space, you are in R6, so you take a point in R6, and I say that the vector field associated to A at this point, VP, is given by a VP. This is a vector in R6, but you should actually shift it to this point, right? And then this gives you this, the vector at this point. And if you do like vary the point, then you get this vector field. Yeah, so actually it's maybe not necessary to write it like this. But you should like use somehow the identification that in a vector space, you have a vector field, that if at each point you have actually a vector in this vector space, and not at the tangent space. No? Is this clear? Kind of, okay. Other questions? Okay, so then actually we should actually clearly state what does it mean actually to be preserved? Because probably you would all say, well, preserved means that it will not change when you act the group, but it's a bit more subtle than this. So, what does it mean? Yeah, what does it mean to be a preserved quantity, a conserved quantity? Meaning, what is the meaning of conserved quantities? Because like the first guess would be to say, well, it means that whenever I assert like mu of m is like this collection of conserved quantities, well, if I apply my symmetry, I should get the same thing, right? Like the conserved quantities, they are the same when I apply my group. But actually, this is not true, unfortunately. In general, this is not true. In general. So the notion of being preserved, being conserved, is a bit more, it's slightly more subtle. But actually, it is not. If you really think about, for example, the last example. So in the last example, what happens? So we see that the conserved quantity is the angular momentum, but actually, to be precise, the conserved quantity will be the vector of the angular momentum in coordinates. Of course, you all agree that like the coordinates of the angular momentum, then it's not preserved. If I change my coordinates, of course, if I change my coordinate system, then the coordinates of the angular momentum will change. Because what is really preserved somehow is this intrinsic object, which is the vector. And so the moment map actually gives you a list of numbers, so it is actually a list in coordinates. So it's actually natural that when you apply your symmetry, you will actually change your conserved quantity, but you will change it in the most natural way you can do. You change it somehow by conjugating what you want to do. I mean, by conjugating by the change of coordinates. Previous example, like mu is somehow the coordinates of angular momentum. And this is, of course, not really preserved, so they change. These coordinates, they change under coordinate change, coordinate transformations. Okay, so now I should tell you what is kind of the most natural action. So this mu of m, this collection of this collection of preserved quantities, it's an element of this dual Lie algebra. So what is kind of the most natural thing you can do on the dual Lie algebra? So it's again a little bit abstract, but it's not too much abstract. So yeah, what is like this natural action of your group on its dual Lie algebra? So what we have a very natural action. We have a very natural action of the Lie algebra on itself, which typically we call adjoint action, and it's just given by the Lie bracket. Like I take x, well, I think typically I call it xi, right? Xi applied to eta is just a bracket. Xi, eta. So this is typically called small adjoint action. So small a because we have a small g like a Lie algebra, and you can like integrate this. If you integrate this, then you get an action of the Lie group on the Lie algebra, which is called the adjoint action. Important, there's a capital here. So what happens like for matrices? For matrices, like this is like the commutator of two matrices, and like, this typically is conjugation. Typically matrix conjugation. Well, and then somehow you have to pass from the Lie algebra to the dual. This is kind of a technical definition. But we will see that in most of the cases, actually, you can again think about it as matrix conjugation. Okay, and then you have like induced action G star. So this is called the co-adjoint action. So it's G on G star. And now actually a bit, so it's called maybe adjoint action. well, actually it's typically written add star. So it's typically written add. Add. This is small add, big add, and this is big add star. And how is it defined? Well, it's defined, like how do you define actually G star? G star is somehow defined as operators on G, linear operators on G. And so I will give you this formula. So if I add star of G, X. So X is an element of this dual Lie algebra. This should be again an element of the dual Lie algebra, and the question is somehow how does it pair with an element? How does it pair with an element of the algebra? Right, G star and G has this natural pairing, applying this linear form to a vector, and by definition, somehow it's a bit an indirect definition. I define this object to be X applied to add G. Applied to Xi. So we already know what the adjoint action is. So well, for some reason there's a minus sign here, there's G inverse. So we know what this thing is. When I fix X, I know what this object is. And I say that this defines you. Again, it's kind of an abstract thing, but typically what happens, in many cases, like typically means G is semi-simple. Actually, it's more general than semi-simple, but semi-simple actually means that you have a killing form which is not degenerate, and then actually you can identify G star with G. And somehow the co-adjoint action then becomes the adjoint action. So co-adjoint action, add star equals add. So that in almost all examples, you should think about this edge-on action as matrix conjugation. And that's exactly what happens for angular momentum, right? You have the angular momentum, it's some vector. When you change your coordinates, this vector will change to, yeah, okay, the vector will change, just you apply this matrix. Yes, I said it's conjugation. The angular momentum is a vector in R3, but actually you should think about this vector as an element of the V algebra SO3. As an element of SO3, yeah, probably as an element of SO3 you should actually conjugate it. Probably, yeah, probably as a vector you justify the matrix. Yeah, sorry. Okay, so this was all just to say what is the natural action. So now comes somehow this theorem, which is somehow the mathematical version of the Noether theorem. So what does the Noether theorem tell us? Well, it tells us that when we have this Hamiltonian action, Hamiltonian, then the moment map is really the collection of preserved quantities. It means that mu of Gm is mu of m, but transformed in the most natural way you can do, which is add star G. So again, it really tells you somehow that this moment map controls all the preserved quantities. This set of preserved quantities is a vector space, and it's actually G star, the dual Lie algebra of the symmetry group. And when you apply your symmetry, you know exactly how these quantities transform. And as a remark, a special case is when your symmetry group is abelian, G is abelian, I don't know, torus or R2 or Rn, and then the coadjoint action is trivial. So mu of Gn is really mu of n. So that's, for example, if you have time invariance gets you energy conservation. The energy is really preserved on the nodes. There's no transformation. Okay, so for those who are interested in exercise, I will not do here. But actually a very natural exercise is when we come back to this linear setting, we had this linear symplectic group. Well, of course it acts on the symplectic vector space. So you should show actually that this is Hamiltonian, and you should compute its moment map. Yeah, compute its moment map. Questions?
I just always get a little confused at this point where sort of the choice of the model or the theory that we're studying pops in. Like, where does a choice of a Hamiltonian or maybe I'm always in R3. Like usually if I think about Noether's theorem, I might write down some action. I would write down a Lagrangian, and then I would look at symmetries of that Lagrangian.
Of the Lagrangian, yes.
And then when I would say conserved, I would mean conserved in time, meaning the time derivative of that charge is 0 or something.
Yes.
But here, where's the choice of the theory or of the Hamiltonian? Or it just seems to depend on the phase space.
That's true. Yeah. Somehow in all this kind of theory we don't specify the Hamiltonian. We start from a phase space which has some symmetry, and yeah, what it tells you somehow is that already in this setting you have conserved quantities, whatever Hamiltonian you pick. But then probably you can somehow specify this, like you can also start from a phase space with the Hamiltonian, so then you have a flow, and you can ask which kind of observables are preserved. But this is actually, this I have actually already seen somehow in this df dt formula, right? It's like hf. So somehow, this answers already your question. Like the conserved quantities are the observables which commute with your Hamiltonian.
And that's often how I would think about a symmetry. So this is somehow different.
Yeah, this would be conserved quantities. That's a good point. Conserved, like a long time evolution. Yes, a long time evolution. Yeah, but we do here somehow a conserved quantity along the orbits of the group. Like, I mean, you could, I mean, whenever you have like a Hamiltonian, you have actually an R action, right? You can always say, okay, I have R acting on MW given by, I don't know, Tm is given by the flow given by your Hamiltonian. Something like this. So you always give an R action. And then I'm pretty sure, like, if you go through all this, I mean, R is abelian. I would guess, we should check this, but I would guess that the conserved quantity you get, well, what is it actually? It should be energy, right? I mean, moment map would be a map to R. This is just H. Yeah, okay, then it does not encapsulate all these other functions, right?
Because here it's important that you like picked a Hamiltonian, like you picked a particular theory, right?
Yeah.
And then you look at the things that commute with it. Whereas in everything you've done until now, it didn't really seem like we picked any.
How would you like see bigger symmetries? I mean, here I have R. I mean, typically, like if, for example, M itself has a symmetry, then probably I could just do this, right? Like G acts on M as symmetries, and R as well, by having this flow. Like G comma M. I would take G comma M and phi T H of M. It's more an extended version. Well, and then like the moment map would give you probably this coordinate would give you the Hamiltonian, like the value of the Hamiltonian, which indeed will not change. And like for any extra kind of global symmetry, it will give you a conserved quantity. But it's true, like this does not really depend on the Hamiltonian. Yeah, this is a much more global thing. Like if the phase space itself has symmetries, this is more specific. But maybe you could think about it in more details. That's very interesting. I mean,
I was just trying to compare it to the usual notions of symmetry I might have. Like,
yeah, that's true.
Like in quantum mechanics, I would think it's stuff that commutes with the Hamiltonian. They're time independent.
It might be, I mean, like the kind of research project, like the small project I had in mind is like to compare this kind of symmetry, this Hamiltonian symmetry, to like the Lagrangian formalism. But maybe one step would be actually already to understand this. Like, Lagrangian formalism, we much more have this time evolution in your mind. So yeah, let's keep it for the very good point. Let's keep it for the like, reflection.
Thanks.
Research, research project. Okay. Other questions? I mean, the examples I gave was like energy conservation or momentum conservation. These are like very general things, right? It does not depend on any kind of Hamiltonian. Like, whatever Hamiltonian you choose, if you have an SO3 rotational symmetry, you have an angular momentum, which is preserved. So yeah, it's actually more general, but maybe then also less concrete. Right? Okay, if there's no question, then let's go to the last part. I mean, now that we have kind of this list of conserved quantities, I said like we want to reduce our phase space. So what is this symplectic reduction, Hamiltonian reduction? there are many different names which exactly say the same thing. So some people would say symplectic quotient, Some people will speak about the reduced phase space, or still another term, more math term. We like to say thanks to people who invented it. So it's Marston, Einstein, quotient. Okay, so what's the construction? So once we have this moment map, from M star, somehow the idea is to fix the values of all these kinds of quantities. So in the first instance, let's fix 0. We consider mu inverse of 0. So that's the submanifold of M. It's a submanifold. I mean, well, it's a submanifold if 0 is not critical. Actually, we don't really need this, but yeah. So again, these are the points in phase space where all these quantities vanish. I mean, the exact value is not very important, right? So let's say that all of them are 0. So you could think that maybe this is already our reduced phase space, because we know, if you are at a point where all these quantities vanish, if you now time evolve whatever Hamiltonian you choose, you know that all these quantities will stay 0 since they are conserved. But actually, this as a space is unfortunately not symplectic. So it's not really what we want to call a reduced phase space. The first remark is, remarks. So first, actually, the remark is what I already said, but it's maybe not that clear, is that this level set, is actually G invariant. It is invariant under the group action. Yeah, maybe to come back to this, actually, I mean, very often in the symmetry group is actually the Hamiltonian, right? So actually, as I wrote it there, he actually always included somehow. This is what I like. Yeah, the Hamiltonian gives you an evolution, but any other kind of symmetry actually also gives you an evolution. So this is G invariant because of this. Right? If mu is 0, so 0 is an element of 0 is the element, the 0 element of the vector space. Then this coadjoint action, whatever it is, it's a linear action, so it preserves the origin. Because at star G of 0 is 0. If your conserved quantities are all 0, then stay 0. Okay, and the second remark is that the subset is not symplectic. It's not symplectic. So it cannot be the reduced phase space. So in general, it's not symplectic. Well, you can, for example, just compute its dimension. Dimension is dimension of M minus, how many constraints we have, the dimension of the group. So a priori, dimension of M is even, since M is symplectic, but the dimension of the group is not necessarily even. And in order to be symplectic, you need an even dimension. And so what you simply do, it's very natural, right? Once you fix your conserved quantities, you have an initial condition, you measure them, so you know whatever the evolution is, that it will stay in this submanifold. But still, on the submanifold, you have these symmetries. So in order to get rid of this redundancy, you just quotient them out. So what we will write like this, the reduced phase space, well, by definition, it will be this level set quotient, which this is this Hamiltonian reduction, or reduced phase space. And the theorem which comes with the definition, which is due to Marston-Weinstein, well, it tells you that this object is a symplectic manifold. Well, with one condition, like if it is a manifold, if Mg is a manifold, then, like for example, what you might need somehow is like maybe 0 should be not a critical point, or maybe this action should be somehow nice. But if this quotient turns out to be a manifold, then it is symplectic. It is canonically symplectic. Well, that's kind of a formula. Maybe I can write it. It's not very important. Like if I denote by pi the projection from the submanifold to the reduction space. So this reduction space is this quotient by G. Then the symplectic form on the space, so this canonically symplectic form, let's call W omega prime. Then the omega prime is uniquely determined by the following property. When you pull it back onto this projection map, then it's the same as taking the omega, the symplectic form on the big manifold, restricted to the submanifold. Determines. Okay, so again, kind of maybe a bit abstract definition. Let's see a concrete example. We'll see how it works. And yeah, before going to the example, just a remark. What's the dimension of this reduction? So the dimension of this M double slash G. What's the dimension of M? So first of all, we take a submanifold, we have dimension of G constraints, then we quotient again by G, minus twice the dimension of the group. And this is even, so you get an even dimensional space. So we have very good. It's like a necessary condition to allow for symplectic structures. Okay. Example. Well, let's take again like a very simple example. Let's take R acting on R2n just by shifting like the first x coordinate. So we have like xi pi. And let's say that t on xi pi it just shifts 1, ex1, p1, and all the rest pn does not change. Just shift by x1. Okay, so we have already seen that the Hamiltonian associated to this is 1. In other words, like using P1 as Hamiltonian gives you this flow along x. So the moment map, so the moment map as well, mu of xi pi can be identified to be just P1. The conserved quantity is P1. Okay, and then let's go through the definition. So what is mu inverse of 0? Well, all points where P1 is 0. x1, comma 0, comma x2, p2. This is the submanifold, and now we should still quotient out by the group action. So the group action tells you that x1 you can put it to any value. So if I take the quotient, I can somehow choose r to n. This would be, I can somehow choose the value of this thing. So let's put it to 0. And this would be like this. So it's like x1, 0, x2, x1, quotiented by r. And then I can identify it somehow with the space of x2, p2, and so on, which is T star of Rn minus 1. Well, Rn, that's R2 minus 2. And this is very natural. Like you have R2n, you have translational symmetry. The conserved quantity is the conjugated variable. You fix it to 0. You still have this translational symmetry, so you can also put your x coordinate to 0, to the reduced phase space, somehow the remaining stuff. And then if you want, you can start again. You can take the x2 shift and reduce it again and again and again. So finally, if you take, for example, Rn acting on R2n, shifting all of the x at once, then this will be a Hamiltonian action, and the reduced phase space will just be a point. In this example, there would be so many symmetries that actually the symmetry determines everything. Okay? One slight generalization. I mean, why should we take 0? Right? I mean, maybe in the initial configuration you measured something which is not 0. So there's this kind of slight modification, slight generalization. So if these conserved quantities have different values, well, we have seen that these values are maybe not exactly preserved, since when you act by your group, there is kind of this co-adjoint action. So what I should actually fix is not like one set of values, but somehow the conjugacy class of these values. So I will take O, co-adjoint orbit, you should really think about it as a conjugacy class of conserved quantities. I mean, of values of the conserved quantities. And then I can somehow play the same game. I take the points in my phase space where these quantities, these preserved quantities, lie in this orbit. So this will be a submanifold which is G invariant, and then I can quotient out by G to get a reduced phase space. So mu inverse of O is G invariant. And then the definition, if you will write it as, we will put actually this O here. We reduce M by G over this orbit. The definition, this is quotient. And again, it is symplectic whenever it's a manifold. So we ask what is the dimension? And this is actually slightly tricky. The dimension, well, of course, you have still the dimension of M. You still like quotient by G, so you should subtract G. But now, I take the pre-image of O. So O has itself some dimension. It might be a point, but it might have some dimension. So you should take its codimension in G. So you should actually somehow subtract team G minus team O. Codimension. Right? And then dimension of M plus dimension of O minus 2 dimension of G. And now what's kind of a bit surprising is it's not completely clear that this is even. We know somehow this is a symplectic manifold, the even dimension, M is symplectic, so this is even, but why should this dimension of the coadjoint orbit be? So the fact is actually, let's extend this remark, so actually O like co-adjoint orbits are actually symplectic. This is something which is not completely obvious. Co-adjoint orbits are always so this is Kirillov structure, Kirillov symplectic structure. If you want to know more about it, it's like a very nice story, but I think it's not necessary. So here, and yeah, then of course if O itself is symplectic, then this is also even. So you have even plus even minus even, you get an even dimensional. Okay. For example, like in the most, like one example would be just matrices, like for example SLN, well, matrices with determinant 1. So the Lie algebra is traceless matrices. If you take conjugacy classes of traceless matrices, they are always even dimensional. Okay, and maybe to finish, let's give a last example. So I told at least mathematicians that one of the aims was to construct interesting examples. So let's construct a slightly interesting, I mean, yeah, it's kind of an interesting example. So let's consider S1 acting on Cn. Following way, alpha acts on C1, Cn, with coordinates by like just shifting the phase. Change all complex coordinates by phase. And I should tell you what this symplectic form is. Well, Cn is R2n, so I can take standard symplectic form. And actually, the standard symplectic form, little exercise, you can write it in complex coordinates like this. It's I over 2 sum dzj h dzj bar. So I use j and not I as an index. Okay, so let's try to do the reduction. So I think in this example, typically it's not really, I mean, it's not a classical example from physics. I think you don't have any intuition of what kind of conserved quantities should be there. I mean, you just change your phase. Well, first of all, I mean, we know that the standard symplectic structure is exact. So let's write like some potential. What did I choose? I choose like to pick this and I get a plus sign. I over 2 sum zj bar dzj. So this is our theta. So it's exact. So even, I mean, yeah, we have not even checked whether this is like symplectic or anything. Let's imagine, like directly check that it's exact. If the action is exact, we know it's Hamiltonian, right? Well, when I replace z's by phase, well, this somehow will put out the phase, but the conjugate gives you the opposite phase, so it cancels out. So the action is exact. Okay, and let's compute like the infinitesimal action and the moment map. And the reduced phase space. This would be the most interesting object. What is the reduced phase space? Okay, so let's see what is infinitesimal action. So if I have alpha is, so it's in S1, well, identity plus epsilon, how to call it, beta maybe. So then, well, then EI alpha zj is E, well, first of all, you can develop the exponential, so it's 1 plus E alpha zj. So I just want to keep things at order 1, so I can start here, and then I have S1. Sorry, the Lie algebra is actually just B, right? It's just a small element. So F1 plus I epsilon beta J. So the vector field associated to beta at the point J, and it's a 1, a 2, it's 1, it's given by I beta Zj. Okay, and then we should plug this. What's the formula? The moment map is given by applying this form to this vector field. So then the moment map at point J applied to beta should be beta applied to x beta. So beta is I over 2 sum Zj bar dzj. You apply this to I beta Zj. So you just get I beta. I times I is minus 1, so minus 1/2 sum theta j bar theta j. Oh, sorry. Beta, of course. And now I'm myself a little bit lost. Okay, let's write it as a vector field. Like as a vector field, it is actually I beta Zj del Zj. So you really have the whole vector here, I beta Zj. So if I write it here, sum del Zj, then you see that the differential, it only pairs about, let's go, k. So j with k gives you a delta function, so you get just j. And now the sum theta j bar is just the norm. It's minus beta over 2. Somehow the norm, well, it's the sum of the norms, if you want. Okay, so the moment map somehow up to some factor gives you the size of kind of this vector in Cn. And so now we know that this is a conserved quantity. So it means that whatever Hamiltonian you take, you will always move on a sphere. And so now the reduced phase space so it's some sphere, but you still have this residual action of your circle. So let's take, for example, so what is M? So it's Cn S1, and let's say, for example, take the unit sphere. So the unit sphere we should actually take as orbit minus 1/2. Because if I wanted this value, I mean, okay. I mean, I take the orbit of minus 1/2, so it means that this should be the set of Zj such that the sum is 1. So this is a sphere, and you still have the quotient by this S1. And this is exactly Cp minus 1. So it's a projective space.
Alex, how much longer do you think you'll need?
I'm finished with this.
Perfect.
Yeah, but
Okay.
since I started a quarter, like...
Right, it's just the,
I mean...
the lunch gods are...
Yeah.
Okay.
Elise told me that they know that we arrive at quarter past.
Oh, okay.
Since we started at 9:15.
Okay. Right, okay.
No, but I'm finished. Like there are different ways to see these projective spaces. I think all of you know. I mean, this is kind of the projective Hilbert space. So you usually would say it's like a ray in this Hilbert space, but actually it's a complex ray, right? So it's actually a quotient by C. And you can use one part of this action to actually first restrict to the unit sphere. The residual action is kind of still changing the phase. So this is exactly CPN. And so this is like, and what have we like gained with all this? Well, we see now, and this was not obvious in the first place, that this is actually a symplectic space. This is symplectic, and it has a name, like the symplectic structure. It's called the Fubini-Studi symplectic structure. So this is what I promised, at least to the mathematicians, to give at least one non-trivial example. So complex projective spaces are real symplectic manifolds. And yeah, I think I'm pretty much done.